wonderful to see a packed room here. Very excited. For those of you I haven't had the pleasure of meeting, I'm Frank Doyle. I'm the 14th provost here at Brown University, where I'm also a professor of engineering and a professor of neuroscience. And it's my great pleasure to welcome you to our annual Lemley lecture. And I'm going to give you just a quick explanation of what the lecture series is. This is the Lemley Family Leadership Lecture Series, and we invite exceptional leaders who are preeminent in their field to come to campus, engage, and inspire the university community. We established this in 2020 through a generous gift made by Wayne C. Lemley, class of 1980 Brown PhD. And our series features highly accomplished scholars, thought leaders, policymakers, and practitioners who will inform, educate, and challenge, advancing Brown's commitment to promoting a vibrant intellectual community. And to introduce today's speaker, I'd like to call up to the podium our Associate Provost for AI, Professor Michael Littman.
Thanks, everybody. I'm so glad everybody could make it today. I actually didn't think this was going to work, that you'd see right through that Yann is not actually here. This is as an April Fool's joke. We just thought it would be really funny to get everybody to come out here. This is CS 1413, Advanced Prompting for LLMs. All right, so first slide. No, okay, all right, that was a joke. All right, so hi, everybody. As Frank said, my name is Michael Littman. He was the 14th provost, which seems like maybe not enough provosts, given how long Brown has been around. But I am the first associate provost for artificial intelligence, which seems like maybe that is enough associate provosts of artificial intelligence. But I wanted to give everybody a chance to kind of get to know a little bit about Yann before he comes on and tells us about his work. So I actually first heard Yann speak in 1988 when he was just 1 year out of his PhD. In his graduate work, he developed the mathematical underpinnings for backpropagation. That's the algorithm that actually makes it possible to train these giant neural networks, or then known as connectionist systems, that underlie chatbots and thousands of other recent innovations today. So not everybody knows that Yann deserves credit for this, but I do, because that's what his talk was about in 1988. And so it was really cool to learn about that sort of in the moment, like while this stuff was actually happening in the early days. That was like the second wave of neural networks. We're now in what we could view the third wave of neural networks. So in the years since, I've crossed paths with Yann many, many times. I've seen him give many invited talks, all of which have been equal parts inspiring and impressive. The inspiring part is that he's a brilliant researcher and his ideas are incredibly deep and insightful. He presents new approaches that are just so cool that you just have to go off and try them yourself, right? So you leave off, at least when you're in a room full of computer scientists, everybody wants to run off and like, is that true? Can I actually try that? The impressive part of his talks is that he actually is a consummate tinkerer, and he often creates live demos to accompany his talks. And if you've ever done a live demo, it is a very dangerous thing to do, and I've seen him do it multiple times. Maybe we'll see one today? He says no. All right, so which I think is the right thing to do, because they can go very badly. So now, if you have followed Yann online, you might have seen that he has very high standards. He will sometimes complain about the status quo, but he's also very, very generous. Just as often as he points out the flaws that he sees, he also creates solutions. So for example, if he's dissatisfied with a piece of technology, he'll create a custom-built alternative. And it may be in the case of creating his own programming language or his own document and image presentation software, like they're really high-quality stuff. And not only does he create this for his own use because he doesn't like what's out there, but he provides it for other people to use as well. And often that's set up as open software, something for everybody to share and everybody use, because that's who he is and that's what he believes. Throughout his career, he has collected a wide variety of distinctions. And I'd like to mention two that might be relevant to the talk, but I'm not sure what the talk is on, so we'll see. The first is that he is a Turing Award winner. So that's the closest thing that computing has to a Nobel Prize. And the award cites his conceptual and engineering breakthroughs that have made deep neural networks a critical component of computing. And that was very, very true when he won the award, and I think it's even more true today. I was actually lucky enough to be on hand for the ceremony, which was very, very cool. And so arguably, winning a Turing Award puts him at the top of academic computer science. But he's now also atop the business world. As of 3 weeks ago, he is the founder of a unicorn company. So that means that it's valued at over $1 billion, and like multiple times more than $1 billion in this case. The company's called Ami Labs, and maybe we'll hear a little bit about that. The name of the company stands for Advanced Machine Intelligence, but it's also the French word for friend. Very clever. So we are absolutely delighted that Yann accepted our invitation to speak to you today. I don't know what he plans to speak about, but I am confident that he will give you something to think about and talk about for days to come. So let's welcome Yann LeCun.
Thank you so much, Michael. So one thing you have to realize is that I've become somewhat famous or infamous for bashing a particular, I'm going to go back to the title slide, bashing a particular aspect of machine learning called reinforcement learning that Michael is actually one of the, pillars of. And so he's saying all those nice things about me, despite the fact that I've been sort of dissing a lot of the field he's been working on, but in a nice way. Yeah. Right, and we overlapped in New Jersey, Michael and I, for a few years. When he was at Bell Core and I was at Bell Labs, they were kind of sister or brother labs. I'm not sure how to say that. And later, when we both joined AT&T Labs, we worked on AI, although in different locations. But in the late 90s, AT&T was probably one of the strongest place anywhere to work on AI. So it's not a completely recent phenomenon that industry research on AI is. Industry is kind of a dominant force in AI research. Okay, so this is a session where I'm supposed to give a short talk. I'm going to attempt to do this. I'm not familiar with the concept, but so that we can have a discussion afterwards, a fireside chat and question and answers. Okay. So first of all, thank you for inviting me. It was a pleasure. And I'm going to talk about world models and about the next generation AI systems, and start by seeing a slide that you just saw, because Michael inadvertently flipped the slide, and it's like AI sucks. Michael said sometimes that I have controversial opinions. That's potentially one of them. So we have AI systems that can write code, they can pass the bar exam, they can win international math Olympiads, but where is my domestic robot? Where is my robot that can clean the house, learn to drive in 20 hours of practice like any teenager? We have systems that can manipulate language, and they fool us into thinking they are smart because they manipulate language. But in fact, they are completely helpless when it comes to the physical world. They can't really handle, LLMs in particular, cannot really handle high-dimensional continuous data, particularly if it's noisy. Think video or any kind of sensor data. Images, video, audio, sensor inputs from measurements, whatever. Financial data, scientific data. And the result is that everybody these days in AI is talking about agentic systems, so systems that can produce actions in the world. And almost none of those systems at the moment are capable of predicting the outcome or the results, the consequences of their actions. It's a very bad way to produce an action if you're not able to predict the consequences of it. In fact, it might be dangerous. And so I don't know, for the life of me, why people believe that they're going to be able to build agentic system by just training them to imitate humans to accomplish tasks without those systems having the ability to predict the consequences of their actions in advance. And that's basically what world models are all about. The other question is, why can't AI systems solve new problems zero shot? If you ask them to accomplish a task they've not been explicitly trained to accomplish, they're not going to be able to do it. So all the robots you see doing amazing things today, they've been trained to imitate humans with enormous amounts of teleoperation data. Or you see robots doing, kung fu dances or whatever, and that's super simple because the only thing you need to know is the dynamics of the robot You don't need to understand how they interact with the world, and that's where things become complicated. Why can't AI have common sense and understand the real world? Like, not like human, like your cat. So never mind humans. What about cats and dogs? They can do amazing things. They understand the physical world. They have some level of common sense. Certainly dogs. And robots don't come close to this. As I said, 17-year-olds can learn to drive in a few hours of practice. And we have millions of hours of training data of cars being driven by people. We could use that data to clone the behavior of humans, train a neural net to basically behave like a human. Yet, despite that, we don't have level 5 fully autonomous self-driving cars that are as reliable as humans. We do have autonomous driving cars. They're not level 5. They can drive themselves pretty reliably, but they can also call home when they're stuck, and their zone of operation is limited, and they use all kinds of sensors, and they require 15 years of very careful engineering to actually kind of do anything. I'm talking about Waymo, a big success of engineering, but hardly learning to drive in 20 hours of practice. So we're missing something big in terms of learning to get machines to learn as efficiently as humans and animals. And we keep bumping into this paradox that Hans Moravec, roboticist in 1988, formulated. There are things that are easy for humans and difficult for AI. And for they don't seem natural. The things that seem easy for AI are complicated for humans, like playing chess. But things we don't even consider intelligent actions, like grabbing an object or manipulating one, we can do with AI yet. The real world is messy, and the people who think that by training LLMs and making them bigger and training them on more language, we're going to reach human intelligence are deluded. Okay. Here's another controversial statement. Okay, there's literally hundreds of billions invested in an industry that basically is counting on the fact that LLMs is going to reach human level intelligence. It's complete BS. It's useful, right? I mean, it's not like those hundreds of billions are wasted, but we're not going to get human intelligence by just getting up LLMs. It's just not happening. So how do humans and animals learn? We learn a lot by observation, of course, quite a bit by interaction as well, and by imitation, by looking at our parents and other humans doing things. But some animals learn without actually the help of other members of their species, and certainly not their parents. Think octopus, they never meet their parents. Think cuckoo birds, never meet their parents either. So humans and animals learn mental models of the world. And in fact, cognitive psychologists have tried to measure the type of concepts that young humans, infants, are capable of learning in the first few months of life. So concepts, very basic concepts like object permanence, the fact that when an object is hidden behind another one, it still exists. We're not born with that. Babies learn this around the age of 2 to 3 months. What's kind of interesting is that notions like intuitive physics, like conservation of momentum, gravity, that takes about 9 months for babies to learn. So if you show a 6-month-old scenario at the bottom of the slide here, where a car is put on a cart and is pushed off on a platform and is pushed off the platform and appears to float in the air, the 6-month-old baby will barely pay attention, whereas a 10-month-old will look at it with big eyes and really fixate because his or her world model is being violated. So I wrote kind of a bit of a co-wrote, I should say, a bit of a vision paper about this with Emmanuel Dupuy, who is a cognitive scientist who actually put together that chart, and Jitara Malik, who's a computer scientist and roboticist at Berkeley, now at Amazon. So how do we reproduce this type of learning, and what is intelligence really, right? There's all kinds of things that are being said about what it is to really be intelligent. And you would think that, with the success of LLM, LLMs are good sort of interpolating information retrieval machines. If they are trained to answer a question, they will answer that question appropriately. They can solve certain problems because they have some special mechanisms that are built in when a particular problem is formulated. But they're not very smart. They can accumulate a huge amount of knowledge. And the reason why they require a large number of parameters and large memory is because they're based on the accumulation of factual or factual knowledge, essentially, not understanding, not much at least. So intelligence, in my opinion, is the ability to accomplish new tasks you've never been exposed to and solve new problems without any prior training or with minimal training, like learning to drive in 20 hours of practice, not millions of hours of examples. So fast adaptation in front of new situation is intelligence. And it's not just adaptation, it's also creativity and, the sort of extensions of adaptations, if you want. Now, the phrase artificial general intelligence, or AGI, makes absolutely no sense. And the reason is because it's designed to designate human-level intelligence, but human intelligence is highly specialized. We don't really realize that because all the problems we can apprehend are problems we can apprehend. But it's, there's no question that we are very highly specialized. Now, there is no question either that machines will eventually surpass humans in all domains where humans are intelligent. That's not going to happen next year, despite what Elon Musk has been saying for the last 15 years. That is going to happen next year. And it's not going to happen in 2 years, despite what Dario Amodei has been saying. It's not going to happen right away. At the very best, we might be convinced that we are on a good path towards human-level intelligence, but not yet at human intelligence within 5 years. But it's going to take a while. And it's almost certainly much harder than we think, because in the past 70 years of history of AI, it's always been much harder than we thought. There's been about 4 or 5 waves, and Michael and I have been witness to this, over the course of the history of AI, of people who said, that's it, we've discovered the secret of intelligence. Within 10 years, the most intelligent machine on the planet will be a machine. And that proved to be wrong every single time. It's going to prove to be wrong this time around as well. I wrote a little, I co-wrote really, I didn't really write it. It was mostly written by the co-authors. This little piece, philosophy piece about, intelligence and really, how we should think about human level or superhuman intelligence. Now, why is it that human level AI will require real world data, sensory inputs, as opposed to just language or text? Okay, take LLM, which is trained on all the publicly available text on the internet. That's typically something like 10 to the 13, 10 to the 14 words. In the case of Llama 3, which was a model that my colleagues at Meta trained a couple years ago, it was about 2 10 to the 13 words. You turn this into tokens. Token is a subword unit, so that's 3 10 to the 13 tokens. The token is 3 bytes. So you get roughly 10 to the 14 bytes to train your LLM on, pre-train. That would take about 400,000 years for any of us here to read through that text if we read 9 hours a day at 250 words per minute. Okay, a lot of data. Now take a human child, a 4-year-old, train on visual sensory data, 16,000 hours of wait time in the first 4 years, which, by the way, is a small amount of video data. That would be about 30 minutes of YouTube uploads. We have 2 million optical nerve fibers going to the visual cortex from the retina, carrying each about 1 byte per second. So that's about 10 to the 14 bytes in the first 4 years, instead of 400,000 years. Is way more information getting to us through sensory inputs than there will ever be through language. And that tells you we're never going to get to human level AI by just training on language. It's just not going to happen, despite what you might hear. Now, of course, video data is much more redundant than language. But that's the point. Turns out all the machine learning procedures that we use rely on redundancy. If you try to train a machine learning system with completely random data, good luck. So what I've been working on with some of my colleagues over the last 5 years, but really the last 15 years, and recently created a company around this idea, is basically enabling the next AI revolution, which would be AI for the real world, using what's called self-supervised learning, which is self-supervised learning for high-dimensional continuous noisy data, such as images, video, audio sensors, etc. And to produce AI systems that understand any environment or system that they need to control, including physical things, so they understand the physical world, but also living things. Systems that have persistent memory, systems that can perform long chains of reasoning, can plan complex action sequences, possibly hierarchically. And systems that can accomplish new tasks zero shot without prior training and adapt quickly to new situations. And finally, systems that are controllable and safe. Current AI systems, LLMs, are intrinsically unsafe. It doesn't matter too much because they're not very smart. And we learn pretty quickly how to use them. But they can't be made completely reliable. Okay, so let me go into the weeds of it. There are two ways to build agentic systems. One is the way LLM are built. You give them what's called a context or a prompt, right? They observe something, which is a sequence of symbols in the case of LLMs, and you train them to predict the next symbol. If those sequences of symbols represent, configuration of the world, and then an action, they will attempt to predict the action. There's no reasoning in that. The way you trick an LLM or an autoregressive prediction system to reason is that you trick it into producing lots and lots of output tokens. And you hope that because it's going to spend more computation producing many tokens, it's going to turn into some form of reasoning. So you train it to go through steps of reasoning. And that's what they call reasoning. But it's not really what reasoning is. Reasoning is a search. When we reason, we search for a solution to a problem. In fact, that's the way classical reasoning in AI has been formulated since the 1950s. I give you a problem. The problem, whether a particular hypothesis can be a solution to this problem, may be characterized by a function. So let's say your problem is to find the shortest circuit of a truck, the delivery truck through cities, the traveling salesman problem. Is a well-formulated problem. There's a well-formulated set of possible hypotheses, which is all the possible orders in which you can go through the cities. And then the function you need to minimize is the length of the path. And so you just search for a solution. Now, in 1958, Newell and Simon, pioneers of AI, wrote a program that they very modestly called the general problem solver. And it was basically that. If you can characterize a solution to a problem and you have a search space for all the possible solutions, the only thing you need to do is search through the solution for one that optimizes that function. They didn't realize yet, because computer science was not invented as a field, that most problems are exponential or NP complete or NP hard. But this concept that inference is a search through a set of potential solutions for a solution that minimizes a particular objective function, that is intrinsically more powerful than autoregressive prediction of tokens. Computationally, it's intrinsically more powerful. You can reduce any computational problem to an optimization problem. You cannot reduce every computational problem to, or at least not efficiently, to an autoregressive token, discrete token prediction problem. Okay, so we have those two categories of AI systems. My money is on the second one, okay? The one that performs inference by search. And that, plus a couple other ideas that I'm going to tell you about, led me to this long-term vision of kind of a cognitive architecture whose centerpiece is a world model. So if you have a world model, what is a world model, first of all? The world model is a system, predictive system, that given the current state of the world, or some representation, abstract representation of the current state of the world, and given an action that you imagine taking or an intervention, can you predict the next state of the world that will result from this action or intervention? If you have such a world model that predicts what the world is going to be after you take an action, you can use that for planning. You can feed the resulting predicted state to an objective function that measures to what extent a task has been accomplished. And by optimization, you can search for an action that minimizes this objective according to the prediction of your world model. You can also put guardrail objectives that are constraints that the system has to satisfy in its optimization search that guarantee that whatever actions are being taken, nobody will get hurt, or the outcome will be good, okay? So a system built around this blueprint is intrinsically safe because it cannot do anything but satisfy your guardrails according to its world model. Now, of course, the guardrails might be inaccurate, the model can be inaccurate, so I'm not saying those models are necessarily perfect, but at least by construction, they will not knowingly produce actions that will, produce dangerous results, let's say. Now, if you have a world model, the classical way to use them in optimal control, a very old engineering discipline, is that you can run your world model multiple times for multiple actions, a sequence of actions, and then you can plan that sequence of actions to arrive at a particular outcome. This is called MPC, Model Predictive Control, very classical. Except classically, the model is written by hand. You want to control an airplane, you can write down the equations of the airplane, the dynamics of the airplane, and that's your world model, okay? You know the state of the airplane, you know the equation, you know the control variables, and so you can just do that. In fact, NASA has been using methods of this type to plan the trajectory of rockets since they've had their hands on electronic computers, which is going back to the 60s. Now, really, the way humans and animals perform planning is hierarchical. If I want to plan my return trip from here to New York, or in this example, plan a trip from my office at NYU to Paris, I cannot possibly plan my entire trip at the lowest level of actions, which would be muscle control every millisecond. I can't plan my entire trip in terms of millisecond by millisecond muscle control. Not just because it's too long and complicated, but also because I don't have the information. I cannot plan the whole sequence of actions in advance. I don't know what the conditions are going to be when I get down on the street and have to hail a taxi. How long am I going to wait? So all planning is hierarchical. We imagine high-level actions, like to go to Paris, I know I have to get to the airport and catch a plane. Now I have a sub-goal, which is going to the airport. How do I go to the airport? I'm in New York, so I can take a taxi or take the subway. Let's say I decide to take a taxi. How do I take a taxi? I need to go down the street and hail a taxi because I'm in New York. How do I go down on the street? Well, I need to go to the elevator, push the button, and walk out the building. How do I go to the elevator? I need to stand up from my chair, pick up my bag, open my door, close my door, walk to the elevator, avoid the obstacles, push the button. At some point down in the hierarchy, I'm going to have all the information I need to just act because I have the information. So I can plan low-level actions. But all of the planning we do is hierarchical. Now, here is a big secret in AI. Nobody knows how to do hierarchical planning. This is an idea. It's not been tested. We're working on it. But you should also work on it if you are interested in this question. Okay, so how are we going to train those world models? Okay, and the natural idea here is everybody is talking about generative models. We should train a generative architecture. All right, let's say we want to train a system to predict what's going to happen in a video. Like, LLMs are trained to predict what's going to happen in the text. You show it a piece of text, and you ask it to predict the next words in the text, right? And there are forms of this where you take a text and you remove some of the words, and you train the system to predict the words that are missing. But an LLM really just predicts future words. Why not do the same with video? Okay, take a video, show a system the first half of the video, train it to predict the second half of the video. I tried to do this for 15 years. The first 10 years of those 15 were basically a complete failure. And the reason was I was trying to predict pixels. Now, as it turns out, when you're trying to predict what's happening in a video, you can, as it turns out, if you train a system to predict the next word in a text, you can do a decent job. You can never predict exactly which word will follow a sequence of words, but you can produce a probability distribution of all possible words in a dictionary. And there's only a finite number. So it's just a big list of numbers between 0 and 1 that sum to 1. We know how to do that. But if you train a system to predict what's going to happen in the video, there's an infinite number of plausible futures. And most of the content there, most of the information in the video is completely unpredictable. So if I take a video of this room, I point the camera to the left here, I turn the camera slowly, and then I stop. And I ask the system, predict the rest of the video. It's going to predict that the camera probably is going to keep panning. There's absolutely no way it can predict what all of you look like. No way. I mean, it's impossible, right? At a pixel level. It can't predict the texture of the ground or the wood panels. It can't predict there is some sort of fireplace at the back. Okay, most of the information in the world is not predictable. But it's very often partially predictable. There is some abstract representation, a formulation of the state of the world that is predictable. So I can predict that, it looks like a pretty full room, and so most of the seats are going to be occupied. I can't predict what you look like, but, the system might be able to predict there is one person in almost every seat. And it's probably going to predict at some point there is a wall, right? Even if you can't predict the details. And we do this all the time. We predict things that are essentially not predictable, but like if I take this object, I put it on my hand, and I tell you, I'm going to lift my finger, you can tell what's going to happen. Okay? If I repeat the experiment, it might fall in a different direction. So you cannot predict exactly at the pixel level what's going to happen. But at an abstract level, you can tell that this object is not stable and going to fall in one of the two possible directions. So what does that mean? This means the idea that you're going to train a system to predict what happens in a video at the pixel level is simply not going to work, because the system is going to spend all of its resources trying to predict things it simply cannot predict. And in fact, we did that experiment. We had a bunch of people going back 10 years where we tried to train a big neural net, I mean, big for the time, to predict a few frames in the future of a video. And we get those blurry predictions because the system predicts the average of all the plausible futures. Some of my colleagues at FAIR also did this with simulated environments. It was a complete failure. Eventually we figured out a way of making things a little better using latent variables to take care of the part of the video that is not predictable. But really it was kind of a failure, except for very simple videos. So about 5-6 years ago, we came up with another idea, and that was derived from empirical results with attempting to use self-supervised learning for computer vision systems to understand images. And what we discovered was that the system architectures that worked the best were not generative architectures, but were what we now call joint embedding architectures. Okay, so you see the generative architecture on the left, okay? You show it an X, and you ask it to predict a Y, potentially conditioned on an action or something is happening. So X could be the beginning of a video, Y could be the continuation, or Y could be an image, and X could be a corrupted version of that image or a different view of the same scene. Okay, and you're supposed to predict Y from X. And that doesn't work very well. A bunch of teams at FAIR and other places attempted to train things like variational autoencoders or masked autoencoders to learn representations of images. And the results were okay. It was super expensive computationally, but it didn't work very well. What actually works is joint embedding. So what is joint embedding? You take both X and Y and you run them both through encoders, and you make predictions, but you make predictions in representation space. So the encoder applied to X produces a representation of X, Sx, which does not contain all the information about X. And the encoder for Y, which may be identical to the encoder for X, produces a representation of Y, Sy, which may not contain all the information about Y. And then you train a predictor to predict the representation of Y from the representation of X. This works really well. There's a lot of self-supervised learning procedures for image and video that actually use this type of architecture, and they work really well. So there's a big issue, though, with this type of architecture. And the big issue is that the system on the right, the joint embedding architecture, can choose to ignore X and Y altogether and minimize the prediction error by just producing constant Sx and Sy. So you have to find a way to prevent the system from collapsing. And this is the difficulty of training joint embedding architectures, particularly JEPA. So what is a JEPA? It's a joint embedding predictive architecture. It's a system of the type I just mentioned. You have variable Y you want to predict, variable X that you observe. You run them both through encoders, which may or may not be identical. And you predict the representation of Y from the representation of X. You train the system by minimizing the prediction error. But you have to also ensure the system doesn't collapse. And one good way to do this is to attempt to maximize the amount of information coming out of the encoders. That sounds great, except we don't know how to measure information. We certainly don't know how to measure a lower bound on information content. We have all kinds of ways to measure approximate information, and they are all upper bounds. When you want to maximize something, you need a lower bound, so you can push up on it, and the actual thing will go up. But we only have upper bounds, okay? So what do? We come up with a good upper bounds, and then we cross our fingers. I'm sorry to say, that's all we have. And there's very deep reasons why we can only have upper bounds to information content. We're never going to find lower bounds, okay? The reason is, to measure information, you have to make some hypotheses about the type of dependencies that you allow your variables to have between them. And what that means is that you're going to ignore certain types of complex dependencies, which means that the measurement of information you're going to get is going to be overestimated compared to the actual amount of information. At least if you believe you have objective measures of information, which actually I don't believe. So it's even worse than that. But there are methods to do this, and there is one that called SIGREG, which I'll say a few words about. And if you want to know more about SIGREG, so it's basically a kind of measure of information that's differentiable that you can use to maximize the information content coming out of a neural net or an encoder or any learning machine. And this was, at least in part, invented at Brown. And certainly implemented at Brown by Randall Balestriero together with me. Where are you, Randall? Right here. Okay, if you have any question about this, talk to him. Okay, he's a faculty, new faculty in the CS department. And so I proposed this JEPA architecture several years ago, maybe 5 years ago, roughly. Since then, there's been something like 1,300 papers talking about JEPA on Google Scholar. So this is not just, Yann's sort of obscure technique now anymore. Okay, so this idea that we need a system to learn abstract representations of observations to be able to make prediction is fundamental to intelligence and certainly fundamental to science. We do this all the time in science. In principle, I could explain everything that is taking place in this room here in terms of, let's say, quantum field theory. Any theoretical physicists here? Okay, one. Two. I mean, physicists will tell everyone here, all of your field are just applied physics to some level, right? Because I can reduce everything to physics. But in fact, we don't, because it would be completely impractical to simulate our brain processes in sufficient details to predict our reactions to this talk by doing quantum field simulation. So we invent abstractions, particles, atoms, molecules in the living world, proteins, organelles, cells, organisms, individuals, societies, ecosystems. And every level of description in this hierarchy allows us to make longer-term prediction than the level below and ignores a lot of details about the level below. That's the essence of being able to understand the world. There's a wonderful quote from Albert Einstein, which is the most incomprehensible thing about the world is that the world is comprehensible. And it could be because there are those abstractions that we can derive that allow us to predict or explain certain behaviors of the world that would otherwise would be way too complicated for us to understand. So the basic idea of understanding the world and modeling it and be able to make prediction is finding good representations, abstract representations that ignore the details that we cannot predict. That's exactly what JEPA does. And of course, that's applicable to AI for science and things like this. So world models should not be world simulators. They are approximations. They should not be digital twins. It's a very popular phrase at the moment. They certainly shouldn't be generative models because you don't want them to reproduce every detail of what you observe. They should not be video generation systems. A lot of people currently use the phrase world model to designate video generation system. That's not what I'm talking about. What they should be is action condition predictors in abstract representation space, preferably differentiable. Okay, so let's say I have a jet engine. Jet engine has typically 1,000 sensors in it. Is there a way I can predict the state of the jet engine from the previous state and the intervention I'm making on it? Let's say it's a chemical plant or a power plant. Let's say it's a patient. Okay, I have a diabetes patient. Is there a way I can treat the patient with a course of treatment that will, bring the patient to a good state with, low blood sugar or whatever? So the point is not to predict every detail, but to predict enough that is predictable. Ignore the details you cannot predict. Same for a robot. We're not going to have useful robots until we have systems that basically can understand the physical world, and currently we don't. You see robots doing Kung Fu. It's super simple because the only thing that's involved is the dynamics of the robot itself, and that we can write equations for. But the interaction of the robot with an object for manipulating it, we don't know how to do that. This idea of world model is really old. It goes back to the 1950s or 60s. 50s in the USSR, 60s in the US, or in the West. The idea that you can use a world model to predict what's going to happen, and then you can plan a sequence of actions. As I was saying, it's been used by NASA since the 1960s. I wrote a couple vision papers about where I think AI research will go over the next few years. The one at the top is a long paper, relatively easy to read, that I wrote in 2022. And there's sort of various versions of this talk, some slightly more technical than the present one. Yeah, let me go back to this if you want to take a picture. Okay, I'm going to use the last few minutes to talk about this SIGREG idea and a model that Randall called JEPA. I have no responsibility in the name. It's kind of a running joke because my boss at Bell Labs, Larry Jackal, whom you know, called convolutional nets back when I was at Bell Labs in the late 80s. He called it LeNet, okay, and the name stuck, and now I have to carry this law everywhere. So the idea that Randall and I, mostly Randall, worked on is the idea that if you want to maximize the amount of information coming out of an encoder, you pass a bunch of samples through it, and you're going to get a bunch of points coming out of it. And if you insist that those points form an isotropic Gaussian distribution, the variables are going to be independent of each other, okay? Because a joint Gaussian, which is isotropic, the variables, individual variables are independent, right? So if you want to maximize information, you have to make the variable independent of each other. And making the distribution isotropic Gaussian is a good way to do this. And it turns out you can do this differentially. You can project the joint distribution over multiple axes, this potentially high-dimensional space. And what you get is a bunch of scalar distribution, one-dimensional distributions, and you can differentiably compute the distance between the Gaussian distribution for each of those projections and the empirical distribution. And you can move the points around so that they collectively become jointly Gaussian. And it works really beautifully. And there's various mathematical tricks to do this. And these are visualization that Randall generated that show, various methods, turning. So Ebb's pulley is the one he used at the right to kind of turn a bunch of original points and move them around so they become sort of joint Gaussian. And more recently, together with Quentin Lelidec, who is a postdoc at NYU, Lucas Meis, who's at Mila, and Damien Sieur, Randall and I kind of worked on this thing called the world model, okay, running joke, which, we can train a world model to, which is action condition, and use it for planning for sort of various tasks, simple robotics tasks and everything. This needs to be scaled up, but we think we have kind of a good handle. I'm not going to bore you with details because I'm running out of time. There are alternative approaches to this, which have so far been scaled up more than this SIGREG le JEPA method. One in particular called iJEPA or vJEPA or Dino v3, which is done by some of our colleagues at Meta, which has lots of applications, probably the best generic image feature extraction system that in existence. But let me skip ahead a little bit. My computer agrees to. And talk about vJEPA. So this is a video prediction system, which is not trained to predict in time, but you take a sequence of frames, you suppress some information about the sequence by blocking some parts of it, not just the future, but like an entire chunk. And then you train one of the JEPA architectures to predict the representation of the full video from the representation of the partially masked video with various tricks. So it's not using SIGREG or any kind of regularization of this type. It's using what's called a distillation method, which I'm not going to go into the details of. And it's not entirely satisfactory in terms of the property of this algorithm, but it scales up and it works really well. And what we have at the end, training this system on a relatively small amount of data, well, a small amount is like 100 years of video, which basically is a day of YouTube uploads. Which is way more than any LLM has been trained on, but that can be trained on like 2,000 GPUs in a few days. So it's not a gigantic LLM. Those systems actually have learned some level of common sense and intuitive physics. You show them a video, maybe a synthetic video, where something impossible occurs, like someone throws a ball and the ball disappears, or it turns into a cube, or it stops in the air. The internal prediction error shoots through the roof when those events occur because the system knows this just cannot possibly happen. So that's really interesting. It's the first time I see this kind of behavior, and I'm sorry the video somehow is not available because the video is on the web and I'm not connected. But anyway, let me conclude. So I'm making a few recommendations here, which make me extremely popular among some of my colleagues in machine learning, particularly in Silicon Valley. Okay, abandon generative models in favor of those JEPA. Abandon probabilistic modeling. So I didn't have time to talk about this thing called energy-based model, which is basically the way to understand the sort of theoretical paradigm with which to understand all of this. Abandon contrastive methods in favor of regularized method. I didn't talk about this, but those information maximization methods are basically a type of training for those energy-based models, which are called regularized. And I put the last one just for Michael, abandon reinforcement learning. I mean, really what I mean is not abandon it, just minimize its use because it's so damn inefficient. But you have to use it, you don't have a choice, right? Okay, right. Okay. Did you just try to Schmidt-Uber me? No. No, you never. No, it's just that RL is inevitable in the sense that there are situations where the only way to improve your performance is to try something and see if it works, and then try something else, and if it works better, adopt that. And RL is basically a sophisticated version of that. But the bulk of the learning takes place when you learn to represent the world appropriately and make predictions. And then learning a task on top of this should be a very fast process, very efficient, that requires a very small number of interactions, which is what allows us to learn to drive in a few hours of practice. So don't work on LLMs if you are interested in human-level AI. And in the long run, the plan for the new company I formed is to become basically the main provider of intelligent systems. It's very modest, okay? Not ambitious at all. And applications of what we're developing really abound in all major sectors of the economy, in sort of academic fields, in physical science and biomedical sciences. Understanding complex systems at a phenomenological level is really what we need for that. And then in industry or economy, healthcare, manufacturing, automotive, aerospace, defense, transportation, logistics, pharmaceutical, et cetera, et cetera. So we're developing AI systems for the real world as opposed to just manipulating language. And we're hoping that eventually we'll build complete intelligent system based on those hierarchical JEPAs and solve a lot of interesting problems. Thank you very much.
Yann, thank you. That was fascinating. And as Michael predicted, you don't pull punches. That's terrific, very candid. So I can't help but noting as a chemical engineer, do we have other chemical engineers in the audience by any chance? MPC is, Model Predictive Control is the backbone of a senior course that's taught to all chemical engineers. And you may know that MPC came not out of the academy, but the private sector. So the Model Predictive Control algorithm was born at a refinery in Texas in the 60s. And it's a wonderful example of algorithms and technology emerging from the private sector first. And then the academics do the theorems and the proofs and show stability and robustness and all those kind of details. I can't help but feel like we're in a moment like that again, where the private sector, Amy in this case, is really leading the way. Help me understand where you see that balance between what private sector brings versus the academy.
So if I count like how much time I've spent in academia and industry during my career, it's about half and half. The first 12 years, 12, 13 years were in industry at Bell Labs, AT&T Labs, NEC Labs for 18 months. Then in 2003, I became a professor at NYU, full-time for about 10 years, and then joined Facebook at the time and was basically half and half between Facebook and NYU for a dozen years. And still now, I'm still a professor at NYU, and I'm also executive chairman of that new company. I don't have any management role because I'm terrible at that. I'm not an operational person. So it's more like, scientific leadership and strategy. But I like that interaction between the two because the two worlds are complementary. They are complementary because the motivation for the people in those two environments are different, right? In academia, you want intellectual impact. In some parts of industry where you have ambitious research lab, like Bell Labs used to be, or FAIR used to be until recently, you also have this ambition of having intellectual impact, not just internal to the company you work for, but also external. In industry, there's a different set of motivation. So it's okay when you're in academia, for example, to work on a technique that you know is a dead end, because it might give you a paper at the next conference or in a journal. And you know you're not going to pursue this, but you're going to get that paper out because it's useful for other people to know, that you can go that direction and maybe some other person will have the idea of pushing it forward, even if you don't. In industry, you don't do this. If it doesn't move you forward to in your kind of main path, which is longer term, you just don't work on it because it's a waste of time. Okay, so this is the exploratory mode of research, which is very much academic. And then there is the thing where you kind of try to make progress on sort of a long-term goal. Early in my career, when I worked on convolutional nets and we applied it to character recognition, right, to handwriting recognition, I had no interest in character recognition. This is not what I was interested in. I was interested in building intelligent machines That had to be done with machine learning because I didn't think I was smart enough to just conceive an intelligent machine, right? It had to build itself. And then, you know, what better domain than perception? If you can do perception, you can do a lot of things. And character recognition was pretty much the only task, perceptual task, for which you could have data at the time. There was no USB camera or anything. And so that was a logical thing to do, and it turned out to be practically useful, even though that was not in the plan initially. There was really a very ambitious long-term plan. So pick a long-term, very ambitious plan and work your way back, and you're going to make progress. Useful things are going to come out of that.
Terrific advice. So staying on the academic front for a moment, you know, one of the challenges, you must see this at NYU, in fact, given your advantage, you must see this globally, is how we think about education in this moment. Because there's the questions of how will these tools be perfused in teaching and pedagogy in the curriculum. But I would argue the more compelling question we should be thinking about is how we train the students who are going out and will enter a world in which there are expectations about competency and skills. What's your vantage, given your kind of 50-50, you know, dual-hatted perspective here, on how we should think about that?
Well, I'm merely a professor, so I don't know anything about education. But whenever I get this question pretty often, either from students or sometimes from their parents. You know, what should I study? Like AI systems are going to be doing everything for us, right? Maybe I don't need to go to college. That's not true. In fact, the trend that we're seeing at the moment, it's very difficult to identify this, particularly in the US, but the trend that we've been seeing over the last decade is that there is more demand for more advanced degrees. Certainly that's true in computer science. There's more demand in industry for people with PhDs, in AI in particular, but not just, than there was just 10, 15 years ago. It's true in the US. It's much more striking in other countries that didn't have this tradition. A lot of countries in the world where doing a PhD was seen as a complete waste of time unless your purpose was to become a professor. And this is still true in a lot of domains, but in STEM, there's a lot of demand from industry for people who have PhDs. Because, why is that? It's because more and more the health of the economy and the growth of the economy relies on technological innovation, and technological innovation relies on scientific breakthroughs. And those come about by people who do research. So research is becoming more and more crucial to economic expansion. What has been one of the main factors of the economic success of the US since World War II is a very, very strong research ecosystem, you know, with universities, public research. Michael Littman can tell you more about this because he was at NSF until recently, which I'm not happy to say the US is currently completely destroying, burning to the ground, which is insane. So there's more demand for more advanced degrees. And regardless of whether AI is going to help us or not, what is that going to change to the way we work? All of us, instead of doing a lot of low-level tasks that AI can do, we're going to be their boss, right? We're going to tell them what to do. It's like, you know, all of us, even at a junior level, will be the manager of a team of intelligent agents kind of doing work for us. We're just going to be managers, essentially. But a good manager knows the low-level technology. So that's the first thing. Second thing is, so study more, not less. The second thing is, what should you study? Now, technological progress is accelerating. It's not a new phenomenon. It's accelerating, but now it's accelerating in a sense that the time constant are very short. So you're almost certainly gonna have to change job during your career because a new technology is going to come in that is going to make your old job completely different and obsolete. You're going to have to learn something new. So what you should do in college and school and grad school is learn to learn, or perhaps invent new things yourself, which is what I was saying with the previous point. So learn to learn. How does that translate? In into what you need to study. Study things that have a long shelf life and that are very fundamental. The joke I usually say, which is not a joke, despite the fact that we're April 1st, if you had a choice between, let's say you're studying computer science, there's a choice between taking a course on mobile app programming and quantum mechanics, take quantum mechanics. You might think it's completely useless to computer scientists, but it's not true. It turns out like all the mathematics that is used for Bayesian inference is the same as statistical physics. So if you want to be able to learn quickly new things, learn the basics, learn fundamental things.
Great advice. Terrific. So maybe delving in a little bit around some of the algorithms you talked about. Again, I'm reflecting back to things like model predictive control and even the applications you spoke of, aircraft engines, the medical problem. These are systems that we do have some rudimentary knowledge, at least at the appropriate scale, as you correctly noted. So we can make sort of first principles, or as a lot of folks refer to, physics-based. So as you and I talked about earlier, there's this sort of PINNs, physics-informed neural nets, and we have people like George Karniadakis in our applied math division here who have pioneered work in that space. Tell me a little bit about how you see intersections between how you bring causality and constraints versus how a PINN approach might do that.
So causality, okay, the bad news is that in physics, causality is not a well-established concept because all macrophysics is time reversible, so causality does not exist in the first place. But at least until you start talking about thermodynamics or collective phenomena, which seem to have a time direction. I think an important point is there are a small number of systems for which you can write down a small number of equations that are more or less solvable, that will allow you to predict the behavior, right, of the system. So you want to predict the behavior of a small molecule interacting with another molecule. You do a simulation of what's called density functional theory. Basically models the density of electrons, around a molecule and figures out like how they stick to each other. It's very expensive. You can only do it with small molecules, unless you have gigantic clusters or GPUs. You can't do it to predict, for example, the conformation of a protein. It's just too complicated. Right? So for a protein, you need to have a specific model that has been trained from data to produce the right result. And of course, those models incorporate some very deep knowledge about the nature of the problem. Like, AlphaFold and ESMFold have, some pretty clear way of representing the conformation of the protein to be able to make the prediction. So there's a lot of knowledge that is in there. But it's a very sort of high-level conceptual knowledge. It's not so very, very detailed to the point that you can reduce to a small number of equations. You have to train the model to make the prediction. Most complex phenomena that we observe are of that nature where you cannot go from the microscopic to the mesoscopic because the underlying processes are so complicated. For example, you might be able to write down a small number of equations that govern the behavior of a neuron in the brain, but that doesn't mean you understand the brain at the system level. Certainly not the learning mechanisms.
Right.
So this idea that you might be able with AI systems to learn a phenomenological model of a complex system that you cannot reduce to a small number of equations in the traditional reductionist approach, I think is very powerful. I'm sure there's a bunch of material physicists here. There's something called a magic angle. You take a monolayer sheet of graphene, okay, single monolayer, bunch of carbon atoms around hexagonal structure. You put another sheet of the same stuff on top of it. You twist it by 1 degree, 1.1 degree, and it becomes superconductor. Why? We don't have reductionist explanation for this. There are theories. But there's a lot of people interested in, developing phenomenological model of material properties that may help us discover, new types of batteries, new ways to, there's some colleagues at Meta that have this really cool project where they're doing so the DFT simulation and this kind of stuff using the supercomputers that Meta has access to generate training data for a system to predict what is the interaction between a molecule of water with a particular material, whatever it is, with the idea that if you might use this model to design a particular material that would facilitate the separation of hydrogen from oxygen in water, you might have solved the energy storage problem. The reason why we can't cover a small desert with solar panels to produce electricity is that we need to store the energy somewhere. And separating hydrogen from oxygen in water is a very good way to do that, if you can make it efficient. You can only make it efficient if you have catalysis. You're a chemist, I'm not. Yeah. Catalysts, they can do this, and basically AI can help us perhaps discover some new ones. That's a really interesting problem. Another problem they're working on is you want to make displays for smart glasses so you can display information. You need optical materials with a very high refractive index. There's one that we know, silicon carbide, is too expensive to manufacture. So what if we can discover a new one that has a high refractive index? They actually kind of made a few proposals for that.
Yeah, I mean, I think you're raising really good points that the complexity, as you've invoked a couple times, sort of dictates how sophisticated the predictive model needs to be. Simple problems may not need more than a mixing the temperature of this room, controlling the temperature of this room. I don't need a quantum model to predict for hours ahead, right? Simple thermodynamics and mixing will do that. So it's got to match the complexity and the objective you're trying to achieve. So I have one more question for Yann. So as a warning to the audience, if you've got questions, get ready to ask them. We'll have runners with mics. But Yann, one of the observations about the moment we're in right now with AI is it feels very disruptive, kind of in our face. People are being forced to confront it in a lot of ways. And I wonder if you could comment on if Amy is successful, if world models are implemented, time scale of, 3 to 5 years. Will this ever truly be sort of an invisible technology that's not, sort of in our face and is seamlessly integrated into human tasks? Or is it always going to have an interface that feels disruptive?
So the kind of stuff we're working on at first are going to be behind the curtain. They're going to be applied to industrial processes. Situations in industry where you have tons and tons of sensor measurements, and you want to optimally control a process, whether it's manufacturing, a chemical process, refinery, a power plant, or maybe some production of a drug of some kind. So that's going to be, business to business, B2B, not sort of in the face of consumers. Eventually, I think all intelligence systems that users will want to use, particularly wearable assistants, are going to be of the type that I'm describing and used by everyone. So there is a future in which all of us will be sort of wearing devices like smart glasses and things like that, which will have AI assistants that we can talk to in various ways, either by speech or through what's called EMG interfaces, electromyogram interface. So basically a bracelet that you wear that allows you to point and click and even type or handwrite. And with a display. And we're going to have those AI assistants with us at all time. We're going to be like, a captain of industry or a politician walking around with a staff of helpers, except those helpers might eventually be smarter than us. I mean, it's already the case, right? It's clear that, the staff of politicians are way smarter than they are, right? At least many politicians.
In many countries, yeah. All right, so we're going to open it up to questions from the audience. Again, if you raise your hand, we'll bring a mic to you. If the runners could, yeah, sure, in the back there. Please introduce yourself and who you are here at Brown or in the community.
Hello, cool. Hi, my name is Sergio. I'm a PhD student here at Brown University. So I'm very interested, very bullish on world models for robotic systems, and that's kind of what my research is all about. So I'm just going to read off of the AMI website, which states, "We can build the future of AI together with industry partners, product developers, and with the global academic research community via open publications and open source." So given how industry research institutions in the past have made the same promise to work with the global academic research community, only to turn for-profit and become closed source once they believe they can monetize their models, can we as a community actually believe that AMI labs will be any different? And is there any way that you can ever ensure that?
So it's pronounced AMI.
AMI, sorry.
It's a French company. I mean, it's a global company, but the headquarters are in France, and so we pronounce it the French way. No, it's a very good question. And I think the option of being closed or open is kind of bimodal. You can't do it halfway. You have to be very open or completely closed, right? You have to be, OpenAI went from one to the other. Google has always been somewhere in the middle. FAIR, the research part of, fundamental research part of AI research at Meta, is slowly going from essentially fully open to not so open. And certainly Anthropic has always been completely opaque, right? So what we plan to do with AMI Labs is, I'm a firm believer in the idea that good ideas can come from anywhere, and they come from the interactions between people working on different assumptions with different motivations in different environments. And what we've seen at FAIR, at least until recently, is that the best way to do exploratory research, including in a university environment, is to host resident PhD students and collaborate with universities. Because, I was telling you that there are exploratory projects that may or may not have, something to follow. And there is sort of the main line, the mainstream of where you want to make progress. Permanent staff in an industry research lab tend to work on this mainstream. If you want to do exploratory, it's very hard to do this with permanent staff because that's taking a risk for them. And so you do this with postdocs and PhD students. And so that makes you in a completely different mode. Now, we have empirical data on this. In 2015, I created the Parisian branch of FAIR Paris. And shortly thereafter, Google DeepMind opened a lab in Paris as well. They didn't have a lab in Paris. They have a Google lab in Paris, but not DeepMind. FAIR Paris has been an enormous success for internal success for the company. A lot of things have been produced at FAIR Paris that have a huge impact on the company. One of them is Llama. Llama 1, the first version of Llama, the open source LLM, was produced by a small team of 12 people in Paris, okay? It's not American technology, it's actually French technology. Paid by American dollars. And then it was picked up by the rest of the company and developed into Llama 2 and 3 and etc. At any one time, until recently, FAIR Paris had 40 resident PhD students. A PhD in France is 3 years because you do a master's before. So FAIR Paris graduates 12 PhD students per year in AI. That completely jump-started the Parisian ecosystem of AI. Two of the three co-founders of Mistral, which is the big French AI company, did their PhD in residence at FAIR and worked on Llama 1, and then left and started Mistral. And I can give you like a dozen companies of this type which were created or helped by people who did their PhD there. What happened was that also we were very integrated with the academic research community in France and just profited from that because of the openness. You compare that with Google DeepMind in Paris, it was not nearly as much of a success because DeepMind is much more secretive. They don't like to have students who kind of see what they're doing internally and kind of take that everywhere else afterwards. And so they could not have, because of IP issues, they could not have resident PhD students. As a consequence, their impact on the ecosystem is much, much, much smaller. So, you want to be in that mode where you progress quickly because you collaborate. And that's the mode we're going to be, at least at the fundamental research level. Now, of course, they're going to be part of the company of AMI Labs. They're going to be more about, technology transfer and product development, and that it's not helpful if it's open.
Great. Thank you for the question. Maybe we can take one up front here. Gentleman with the sunglasses on his head. Do we have a mic? Yeah.
Hi, I'm Takis Dimitrakopoulos. I'm a senior from Athens, Greece, studying applied mathematics and classics. Thank you very much for your time here today. I wanted to ask you the following. You argued in your presentation that a lot of the LLMs can't achieve human-level intelligence because they lack, among others, persistent memory, grounded experiences, the world models that AMI is going to develop. And I wanted to ask that if an LLM eventually passes every benchmark we design, at what point does the distinction between actual cognition and true reasoning, sophisticated pattern matching, becomes philosophically meaningless? At what point does that just equate to moving the goalposts?
Okay, so as I said, I think intelligence is not a collection of skills or an accumulation of knowledge, but an ability to solve new problems that you never faced before. Let me take a concrete example. There is no way to design a set of questions or problems that the next generation of LLM will not be able to solve. And it's very simple. It's like as soon as you come up with a set of questions that LLMs cannot solve, you just integrate them in the training set, and then the next generation is going to solve those questions. I've been at the receiving end of this multiple times when people ask me, like, is there any question that an LLM cannot answer? I say, yeah, like we have an intuitive understanding that if we put an object on the table and we push the table, the object will move with the table, right? That's very simple physical intuition. So I said that during a Lex Friedman interview. And 6 months later, someone asked the question to GPT-X. And of course, GPT, whatever it was, 5, answered the question correctly. And so a lot of people on Twitter, haters on Twitter said, oh, Yann LeCun is out of it, like he's totally stupid. He claims those things that are false, blah, blah, blah. But it's very simple. The GPT version in question was trained with that question. That question was publicly available. OpenAI has thousands of people actually kind of listing all of those questions that might be asked. And because I asked that question to Lex Friedman, you had immediately hundreds of people trying that on ChatGPT. And so now OpenAI has the data of people asking this question. And of course, they're going to train it to actually answer that question correctly. There's this example recently that there's someone that comes up with those questions that LLMs don't answer properly. He said, I need to wash my car, and the car wash is 100 yards from my place. Should I walk? And they all say, yes, you should walk, because there's no point taking your car, and it gives you a long list of reasons why you should not take your car for 100 yards. Of course, those systems don't have any sort of physical intuition, right? Which is why they answer it this way. You can be sure that the next generation LLMs is going to answer this correctly, because that is now part of the training set. So there's not going to be any finite test that is going to determine whether a system is intelligent or not, because it's just information retrieval. The big question is, here is a new problem you've never seen. Can you solve that?
Thank you.
Thank you for the question. Yeah, we'll take one right here, the gentleman in the tie.
Hey, my name is Dominic. I'm a Brown alum. And one thing I was wondering, so do you believe there's any place for large language models in amplifying the abilities of world models, similar to how different specialized regions of the human brain cumulatively amplify human cognitive performance?
Okay, we do have an LLM in our brain. We have a small part of our brain right here behind the ear called, it's about this big, it's called the Wernicke area. That's what allows you to turn language into thoughts. And then there is another one right in front of it called the Broca area, also about this big, that allows you to turn thoughts into speech. You can't speak if you have damaged Broca area. Those things popped up in evolution maybe 1 million years ago, maybe a bit more. They cannot be that complicated because they are so recent and so small. You combine that with your hippocampus, which is where you store a lot of declarative knowledge, and that's your LLM, okay? But your intelligence is this. Okay, we have a good handle on perception. That's the back of the brain. But like the front of the brain, that's your world model. That's what you reason with. And that's, you know, what we attempt to perhaps emulate with AMI labs and world models, but LLMs just don't have that.
Thank you.
All right, do we have one further back? Let's take advantage of the back of the room. Gentleman in the black jacket there with the glasses, yeah.
Thanks for the talk, Yang. I'm TJ. I'm a PhD candidate from Biostat department. I think I have a more concrete question about the world model itself. Like, how you define the state in the model? Like, how far from the state is that latent from what we observe? And could it be achieved by, like, I have a fancy decoder design or more dedicated loss function design? Like, it's not something beyond current deep learning framework.
Okay, so what is the state? That's a good question. The state is not an objective property of the phenomenon you're observing. It's an abstract representation that serves the purpose of making predictions. And the state that you will use to make predictions in 1 millisecond, with a 1 millisecond time frame, is not the same as the state you're going to use to make predictions an hour from now. And so what you need to, what the JEPA or similar model need to represent by the state depends on the type of, the horizon of the prediction that's supposed to do. The longer term prediction you're making, the fewer details you can keep in the state, because there are things you just cannot predict long term if there are too many details, right? You cannot predict the individual trajectories of molecules in this room. That's just too much computation. Also, measuring the initial state would be very hard, impossible, in fact. And very quickly, the simulation will diverge from reality. But if your purpose is to, predict the pressure in this room as a function of temperature, you can do that. PV equals nRT. You don't need to simulate every individual molecule to be able to predict that. Or similarly, if you are an aircraft designer, you want to design the airfoil of the wing of an airplane, you can do computational fluid dynamics. You don't simulate every molecule bumping into each other and onto the airplane. You model the state of the air in a little cube by velocity, pressure, and temperature, and then you solve Navier-Stokes equations. So everything we do in prediction requires to find an abstract representation that eliminates all the stuff we cannot predict and allows us to make prediction at the time scale that we are interested in. And so the way JEPA is built is that it finds this trade-off between maximizing the information content of the representation, but yet only preserving things, information you can predict. And then depending on the horizon at which you train the prediction, you will get different level of details in the representation.
Great. Maybe on the row here, the lady with the glasses.
Thank you. I'm Sonia. I study anthropology and computer science, so an interesting mix when it comes to world models. I wanted to ask you how you approach building teams at AMI Labs and in general people who work on world models, because even with LLMs, we talk about lack of diversity, right, and lack of variables that go into building a good response. World models feels exponentially larger than that. So when do you stop building your teams representation-wise, but also when do you stop building world models variable representation-wise? Thank you.
So the world model itself, the type of things I will capture depend on the data it's trained on. And most of this data is, physical measurements and stuff like that. Of course, you could also imagine training world models that try to, predict human behavior. In fact, we have a name for it. We call it mental world model. Like if you want the dialogue system to be useful, like let's say a system that is supposed to help students learn particular material, you want that system to be able to have some idea of the mental state of the person he's talking to. and then have some way of predicting what is going to be the mental state of that person once I tell the person a particular piece of information. Is that person going to be able to absorb that information and learn something from it, or just completely ignore it? So that's called mental role model, and there we start to get into like questions of who can receive what type of information, etc., what biases are, etc. I believe there was some other question about implicit question, at least in your question, about the composition of the staff at AMI Labs. Yeah. What's the proportion of women in your CS class? Say again? 40%. That's great. That's awesome. The national average is closer to 20%, probably between 15 and 20. And it's been the case for quite a number of years. It went down from about 40% in the 80s to between 15 and 20 nowadays. Some universities like Brown, CMU, and others, make a point of trying to kind of balance. There is no particular change of proportion at the graduate level. So the proportion of women in PhDs is roughly the same as undergrad. So there is no leak in the pipeline at that level. But there's clearly a small number of women getting into that pipeline nationally, even if it's better at Brown. How do we fix that? Like, why is it that over the last few decades we've reached parity in things like medicine, law, and various other domains, and not STEM? I don't have an answer.
It's a challenge. I'm going to take the liberty, we're just about out of time, to pose one last question, which kind of feeds, in particular, the background of a couple of our questioners here that might shed light on what we're doing differently at Brown here. And you've heard these dual interests in humanities and CS, in social sciences and CS. And so my question for you is, a little bird told me you have a particular passion in music. Tell us a little bit about that side of your own duality in marrying humanities and tech.
Yeah. Since I was in middle school, as a matter of fact, and high school, I played in a Renaissance band. So I played Renaissance and Baroque music, so various wind instruments. And I also played Breton folk music. That's pretty obscure.
Proto-folk?
Breton. Okay, Brittany. You know about Brittany, right? So Brittany is the western part of France. And the tradition there it's a Celtic population, the same origin as Ireland and Wales and places like that. Traditionally in Western Brittany, didn't speak French, but spoke a Celtic language called Breton, similar to Welsh. And the musical tradition there is Celtic. So there is like a very distinct culture there. And I used to play that music. And it's very similar, in fact, to Renaissance dances. The sort of not the dances that you dance in the courts, but the dances that everybody in the villages would dance in Renaissance, where the popular folk dances are inspired by that, basically direct descendants. So that there was kind of a connection between those two things, and it taught us how to play Renaissance music at the right speed. Almost the only 2 times you can hear Renaissance music in the US is if you go to a Renaissance fair or at Christmas time. Mm-hmm. They play fake Renaissance music with modern instruments as if they were Christmas songs, and they play them about 3 times slower than they should. It drives me crazy. Okay. But then, after I came to the US, I was always a fan of jazz and various versions of improvised music. And I always thought the intellectual process of improvisation as mysterious to me. And so I decided that I should learn to do it, to figure out like what's the deal. So I tried to, play jazz. I'm a terrible performer, but got interested in this. But in fact, I would tell you something. I got interested into electronics, and my undergrad is in EE. And I got interested in electronics and computer science eventually through music. I wanted to produce music with computers. And also I played with synthesizers. My cousin, who was a little older than me, was an aspiring electronic musician in the 70s. And I knew a bit of electronics when I was in high school, so I would hack his synthesizer so that he could produce new sounds. And I keep doing this. I have like a whole bunch of synthesizers in my home. I'm a terrible performer again, and I don't play keyboards. So because I don't play keyboards, I built myself electronic wind instruments with which I can control my synthesizers. Okay, that's my hobby.
Far out. Wow, what a renaissance man. Please join me in thanking our wonderful Lemley speaker, Yann LeCun.
Thank you.
And in the spirit of his comments about the Celtic language, one of the very few words I know in Gaelic is sláinte, which is Gaelic for cheers. So please join us for a reception out in the lobby there.
In fact, in Breton, it's Yared Mat.
There we go.
Okay, before you go away, I'm going to take a selfie, okay? So don't move.
Come down here with Michael. Terrific. Thanks again.